So have a, are we all better? Yeah. Hey. All right, so I have a Ferris wheel. I haven't been on a Ferris wheel in a long time, and I looked up the size of different Ferris wheels last night. Of course, all you ever find out is like the biggest ones in the world and everything, and they're massive. Although Orlando has, I guess, the 10th largest Ferris wheel in the world, second largest one in the United States. Vegas has the largest one in the United States, 122 meters tall. Anybody scared of heights? I am not necessarily scared of heights, but I am becoming more and more mortal as I get older. So 122 meters looks pretty tall. It's gotten stuck twice, and once was a software glitch that required people to be rescued over the span of 3 hours. That would probably be unpleasant. Regular Ferris wheels that you see in like the state fairs and such, they're designed to try and make you feel like you're being thrown out of them. So if you're sitting in one of the chairs, which is just usually a bench with a bar in front of it, legs like that, they're going to go this way often so that you feel a little bit thrown out towards the top. They can run them in either direction, though. I'm not sure if you guys are aware of that. It's just a choice of the operator and the particular fair. So they can have you coming up this way as well if they wanted to. It's just different kinds of choices. Let's go with a kind of a straightforward Ferris wheel that's 10 meters in diameter. 10 meters in radius. And let's assume that a standard Ferris wheel like this one takes a rotation and a half to get the full speed. I'm giving you information. Takes a rotation and a half to get the full speed. And at full speed, you feel half your weight at the top. Okay. At full speed, you feel half of your weight at the top. What would be the angular acceleration in radians per second squared required to make that happen? And how long does it take to get to full speed? Okay. So 2 questions. I'm asking you to find alpha. I'm asking you to find time. I gave you omega naught, because we assumed we started from rest. And I gave you delta theta during the interval when we're speeding up, which was 1.5 rotations. But I didn't give you anything else directly. I gave you something indirectly. I said that when you were at the top, on the chair there, at the top, you felt half of your weight. Now, this detail, this is where I think you guys tend to fall down, because you don't always remember stuff from a prior lesson. But your apparent weight is the normal force acting on you. Okay? Your apparent weight is the normal force acting on you. You can't feel your weight. You can just feel the effects of your weight on conditions around you. So I gave you the size of this person's normal force. Now, you may not know what to do with that, and that's reasonable. But there should be clues as to what you're going to do with this. For example, the first clue, I sense a circular motion problem. Do you sense a circular motion problem? All right, so that's a good start. A circular motion problem is very likely to center on the themes we've seen for circular motion, which could be this kind of stuff, rotational kinematics. But first semester, it was always the same thing. It was a net force equals MAC problem, and that's what this is. This is a net force equals MAC problem. So I'm helping you at the beginning, but then I'm going to stop and let you guys go to work. So my last bit of help is you should look here and kind of figure out what forces are acting on the person when they're at the very top. And that shouldn't be much to deal with. Downward force for weight and upwards normal force. I've given you enough information, I'm hoping, that you could fill in the gaps because you could use this part to figure out this. And from there, it's a kinematics problem. So I'm going to stop right now. I'm expecting you to confer with the people around you. And then I'm just going to draw tables, and tables will tell me different answers. And I'm going to go in this order. I want to know the angular velocity at operating speed. And then I want somebody to tell me the angular acceleration in radians per second squared. And then I'll ask for the time. That's the order I'm going to go in. I'm just going to pick 3 tables to tell me. Everybody got it? Give it a shot. And AC, I know you guys remember, is V squared over R. But we also know that V is equal to omega times R. So you can write this as omega squared times R. These are the 2 different ways of dealing with centripetal acceleration from first semester. I don't know if they're both on your equation sheet. I'm pretty sure there's only one is. But I think one of these would serve you better here. You know, this one. It would be a more direct route to your answer. No, because we're not setting these 2 things equal. We're using one of them as a substitute for AC.
So AC equals VT.
And so I would take this and put this here. AC does not equal VT. This R does not cancel. These are just 2 different expressions for centripetal acceleration.
So
I'm not suggesting you set them equal to each other. If you do set them equal to each other, you get this. Okay. There are 2 forces, right? There's the weight downwards, normal force upwards. We good? So did you do net force equals MAC, which means, and be careful, I'm making downwards positive. We always make the towards the center the positive direction. Mg minus half mg equals m omega squared r. All good there? Any questions about that? I can cancel out all the m's and get half g equals omega squared r. Now, you guys were all writing down. If you couldn't do these things and you didn't ask me a question, I was walking around. That lays heavily on you now. I'm just doing this because somebody seems confused about units. So 1/2 times 10 meters per second squared equals omega squared times 10 meters. The radius of the ride was 10. All good? So if I were to say, write this as 5 meters per second squared equals omega squared times 10 meters. If I divide both sides by 10, the meters is going to cancel, giving me 0.5, nothing on top, divided by second squared. Remember, and I've said this to you, and I know you were supposed to know some of this from pre-calc, but you may not. If you have an angle measure that works out to be unitless, it's radians. So that makes this radians, not rotations. And that equals omega squared. And then when I square root both sides, I'll get 0.707 radians per second. So if you are working on something you know to be an angular value and the units cancel out, it's in radians now. Radians are actually a unitless quantity. So now we've answered the first question. Arguably the harder of the parts of this. But what this also means is that if you're going to use this over here and put in your 0.707 radians per second, the only way you can get either of these values is if you convert everything to rotations or convert everything to radians. But I expressly wanted this in radians to force you to make a choice. So you'll have to convert this to radians. So now that we've got everybody to the motion part of the problem, hurry up and finish the motion part of the problem, because this is the only part that's kinematics. I address, and this is one of them. I need to convert 1.5 rotations into radians. And again, sometimes I get surprised by things. You're right, there's nothing in the denominator here, but we're going to use unit multipliers. There's nothing in the denominator, just put a 1 in the denominator, turn it into a fraction, if that's bugging you. And then from here, it's still just putting in a conversion fact, and you're wanting to get rid of rotations and be left in radians. And although I know I keep saying radians is a unitless quantity, I think it's better for your psyche if you just put things down and put radians there to let you know. That way you know what you're working with. And that might be why the rotational stuff is more complicated, is because of this dealing with radians, but it's just a measure of angle. So I think part of it is you don't have a sense of scale, and that could be it. But one rotation is 6 radians, right? 2 pi is about 6. So when you're working with this, since you don't have a good sense of scale, you can get a number for radians, and it can mean anything because you don't have a good proportionality for what it means. So I would just start to encourage you to think that a circle is 6 radians, and it gives you a sense of scale, so you can kind of know if your answer is right. And I'm expecting that 1.5 rotations is probably going to be 6 plus half of 6, or something around 9, because a rotation is about 6. But we put our conversion fact in here, the rotation still cancels, and we'll be left with, what is it, 9.4? So in making 1.5 rotations, you've traveled 9.42 radians. It's just be like 360 plus 180. It's the same idea. Radians is just going around in a circle, just how much. So we now have all of our values in compatible units. And again, it's just trying to be in compatible units. Like, you couldn't mix centimeters and meters before. You can't mix rotations and radians here. You got to pick one and stick with it. I'm going to encourage all of you who are novices here and have not done this before. Radians is the safest unit to be in, because any of these all of those require radians. So if you're in radians, you are safer to use that value elsewhere. If you're in rotations and degrees, you're not. Rotations and degrees are arbitrary. They're not mathematical in nature. I'm curious. Wow. The kinematics of this is not the hard part, clearly. So have we gotten to the kinematics part? Because, boy, it took a lot of time to get here, and I'm a little bit nervous about it. So let's see. Pride Rock, can you tell me what the angular acceleration is? 0.027 radians per second squared. That sounds great. Which relationship did you use to do that?
I found the angular speed, and then I just did the Q-A delta theta.
Excellent. Yeah, that'd be the way I would do it. All right, and Gotham, can you tell me what you guys got for time? 26 point. Seems really high. But if that's what you got, that's what you got. 26.9. 26.66. What relationship did you guys use? You could have used any of them. Did you use the most direct route? Yeah, that'd be the most direct route. That's, of course, assuming this is the right answer, but that'll do it. All right. Wow. Maybe we need more practice than this. So shall we do another practice? All right. So again, we have 20 seconds starting from rest to get up to your operating speed on a 3-meter children's ride. I'd like the angular acceleration in radians per second squared. And I'd like to know the centripetal acceleration of the riders if they're 3 meters from the center of rotation.